So far, we have taken examples of electrophilic aromatic substitution reactions such as halogenation, bromination, and chlorination. We then learn about nitration, and then later on, we learn about sulfonation of benzene to give benzene sulfonic acid. Let's now see how we can attach an alkyl group to the benzene ring in an alkylation reaction. Benzene can actually be bonded to an alkyl group in what's called Friedel-Crafts alkylation. That's when benzene reacts with an alkyl chloride in the presence of aluminum chloride. So let's draw a general scheme for the reaction for the Friedel-Crafts alkylation. So this is benzene, and then RCl in general as an alkyl chloride in the presence of AlCl3 as a Lewis acid catalyst, and alkyl benzene is actually formed. That's when it's bonded to an alkyl group. Remember, R is alkyl, okay, and this reaction is called Friedel-Crafts alkylation. So Friedel-Crafts alkylation involves a reaction of benzene with an alkyl chloride in the presence of aluminum chloride. Let's take an example. When R is a simple alkyl group possible, which is a methyl group, so we're talking about chloromethane, for example. So if benzene reacts therefore with CH3Cl chloromethane in the presence of AlCl3, then toluene is actually formed, or methyl benzene that is formed. If you look at the structure of toluene, you can easily spot or identify, if you like, the electrophile that's required or that should form as an intermediate in this reaction. And that electrophile that's required is this carbocation, this CH3 plus, a carbocation where carbon has a positive charge. So that carbocation should form, that methyl cation should form when chloromethane reacts with aluminum chloride. Let's draw the structure of chloromethane, and there it is, and this is AlCl3. Remember, aluminum chloride, just like iron before in the case of halogenation reactions, this acts as a Lewis acid. So AlCl3 is a Lewis acid. And of course, Lewis acid, a substance that requires a lone pair. And that lone pair will come from a Lewis base, such as a halogen. So this is the Lewis base. So it's a reaction between a Lewis base and a Lewis acid. We take one of the lone pairs on chlorine. We make a bond between chlorine and aluminum, as indicated by that K arrow, and then we get something like this as an intermediate. Where chlorine has a positive charge. Now, the CCl bond is then broken to give electrons to the positively charged chlorine, as shown using this scale arrow. Now, this gives CH3 plus or this carbocation as an electrophile, plus AlCl4 minus as a byproduct in this reaction. So this is really the electrophile that we identified earlier. This is the electrophile that reacts with benzene. Now benzene will come in and it does react with this carbocation in a slow step initially to give this initial carbocation here. And of course, remember that carbon always carries a positive charge. That's because it loses its electron share as a result of this step. Now, conjugate base should come in now, like AlCl4 minus. It comes in, it takes off that proton, and the hydrogen bond is broken, and a carbon-carbon double bond is formed. Now, this gives the final product, which is methyl benzene or toluene. So this is an example of a Friedel-Crafts alkylation. It's an alkylation, of course, it's an alkylation reaction because the result is an alkyl, or the product is an alkyl benzene. That's when benzene reacts with an alkyl chloride in the presence of aluminum chloride. Remember, aluminum chloride is a Lewis acid chloroalkane, if you like, or alkyl chloride behaves as a Lewis base. The required electrophile in this case is actually a carbocation, which then initiates the reaction with benzene, eventually to give alkyl benzene. So this is a methylation reaction, an example of a Friedel-Crafts alkylation.